to part 2 of the Chapter 6 Comprehension Check. For this part, we're going to focus on balancing equations and the main types of chemical equations. So we're going to start with question number 7. It tells us that nitrogen gas and hydrogen gas are reacting to make nitrogen trihydride gas. What is the balanced chemical equation? Well, they don't give us anything except for words, so we're going to have to write it out and then balance it. So it tells me I have nitrogen gas, and I want you to remember that nitrogen is a homonuclear diatomic, so it's not going to be just one N, it's going to be a 2. Now it's telling you the phase is a gas. And so the next part of the question, it says, and hydrogen gas. Guess what? Hydrogen is also a homonuclear diatomic. I have these two gases and they're reacting together to make nitrogen trihydride or ammonia. You may have smelled ammonia before. It's sometimes used in cleaning supplies and it has a very powerful smell. And so it tells me it's nitrogen trihydride. So tri means 3. So I have 1 nitrogen and 3 hydrogens, and this is also a gas. So we've written the equation, but you should always balance equations. Even when your book gives you an equation and it has coefficients outside so you think it's balanced, you should always check it. Balance this, I'm going to write what I have. So I have just nitrogen and hydrogen in my reactants and nitrogen and hydrogen in my products. And here I actually have 2 nitrogens and 2 hydrogens. So I'm going to put a 2 here. As far down here, products, we have 1 nitrogen and we have 3 hydrogens. So we can see that 2 nitrogens are not going to produce 1 nitrogen. 2 nitrogens are going to produce 2 nitrogens. So we have to change this because we don't have enough. Now I can change this. I cannot change the compound. I cannot change the chemical, the NH3. I cannot change that. But what I can change is how much of it is it producing. So I'm going to not make 1. There's an understood 1 here. What if I put a 2 and it made 2 of this molecule? So then I would have 2 nitrogens, and each molecule still has 3 hydrogens, but since there's 2 of them, there's a total of 6 hydrogens there. Nitrogens are balanced, but the hydrogens are not. So if I'm going to finish with 6 hydrogens, I have to start with 6 hydrogens. So I can get this to 6. Since each compound has 2, if I have 3 of those compounds, I will have a total of 6 hydrogens. And so now we have 2 nitrogens starting, 2 nitrogens ending, 6 hydrogens starting, 6 hydrogens ending. This is going to follow the law of conservation of mass, and so this is a balanced chemical equation. For question 8, we're going to be doing the same thing. We're going to be writing an equation from a word problem and then balancing it. So I'm going to read the word problem first. It says, many outdoor gas grills burn propane, C3H8 gas. It comes in a lot of times this gray metal canister that sits underneath your grill. This propane gas reacts with oxygen in your air, making gases carbon dioxide and water vapor. That's actually the combustion reaction that happens in your grill. What is the balanced chemical equation for this reaction? So let's just start with the first thing it tells me. It tells me I have C3H8 gas. Then it says that it's reacting with oxygen in the air. So I'm adding it to oxygen. Please remember, oxygen is a homonuclear diatomic. I told you you were going to need to know those. And it says it's producing carbon dioxide. That's a gas that we breathe out. And it also says water vapor. And so I'm putting the G for gas because it says it's a vapor. I know it's a gas. So I am going to now balance this equation. So on my reactants, I have carbon, hydrogens, and oxygens, and this is the same down here. The first thing you're going to do is you're going to determine how much of each of these elements we have. So we have one of this whole compound, but each molecule has 3 carbons and 8 hydrogens. I also have one oxygen molecule, which has 2 oxygens in it. So in the products, I'm producing 1 carbon dioxide, which has 1 carbon in it. Hydrogen is found in the water, and each water has 2 hydrogens in it. And then for oxygen, I'm actually going to find oxygen on 2 separate places. So we're just going to add it together. So we have 2 here plus the 1 there. So we have a total of 3 oxygens. So my carbons are not balanced out. My hydrogens are not balanced out. And neither are the oxygens. A lot of times students have a hard time figuring out what do you start with. Well, I like to say that if you have an element and it's by itself, so even though it's oxygens with another oxygen, I only have oxygen here, save him for last. Do it last. The other one that you'll get in the habit of doing towards the end is going to be water. So let's mess with the carbons first. I have 3 carbons. I need to produce 3 carbons, right? If I start with 3, I have to end with 3. Now remember, when we balance, we don't mess with the subscripts. We only mess with the coefficients or the numbers in the beginning. So I can't change carbon dioxide. Carbon dioxide is the gas that this reaction produces. But I can change the number of carbon dioxides that I'm going to produce. Now if I produce 3 CO2s, I have now 3 carbons. And it also changes my oxygen. Because I have 3, and then each one has 2 oxygens. So that's a total of 6 plus the 1 makes 7. Now my carbons are balanced out, and we said we were going to do oxygen last. Let's look at our hydrogens. So I have 8 hydrogens on this side, and I am only currently producing 2. So I need to make this produce 8 hydrogens down there. So what I'm going to do is, since each one molecule produces 2, if I use 4 water molecules, I have 4 water molecules, since each one has 2 hydrogens, I'm going to have a total of 8 hydrogens. Now, when I put this 4 here, not only did it change the hydrogens, but it also changed this oxygen. So it means on this part, I have 4 oxygens. And if you'll remember, I have 3 times 2, which is 6. So I have 6 oxygens here and 4 here. So I have a total of 10 oxygens. Now we're going to do those oxygens that we've been waiting to the end. So I got to get this O2 to have a total of 10 oxygens. So if each one has 2 oxygens, I need 5 total. 5 times 2 is 10, and that will make this be a 10. And we're left with 3 carbons, 8 hydrogens, and 10 oxygens. And that is your balanced chemical equation. For question number 9, they give it to you in the chemical equation, not the word equation, which those are kind of nice. Takes a step out. So we have in our reactants, we have carbon, oxygen, and hydrogen. And we're going to balance, let's write down what we have of each starting. So for carbons, I have this carbon monoxide, and I have 1. And there's 1 carbon in the compound. For oxygen, we have 1 oxygen. And for hydrogen, homonuclear diatomic, so I have 2 hydrogens. In the products, we have 8 carbons. For oxygens, oxygen's only found in the water, and each water only has 1. So we have 1 water, so we only have 1 oxygen. And as far as hydrogen goes, we actually have hydrogens in the C8H18 and in the water. So here we have 18 hydrogens, and here we have 20. So we already have some bigger numbers than we've previously had balancing these equations. I told you to leave the element that is by itself for last. So the only element we really have by itself is hydrogen. So we're going to do hydrogens at the very end. So let's start with carbon. Carbon is a great one to start with. Since I'm ending with 8 carbons, I have to start with 8 carbons. So I'm going to do that by putting this 8 right here. And this means I have 8 of this molecule. Remember, when you are balancing, do not mess with subscripts. So we have 8 carbons. And it's also going to change the oxygens. And there's 1 oxygen per one, so we have 8 oxygens. So now let's do the oxygens. Remember, we're saving the hydrogens for last. And so I have 8 oxygens over here. I want to try to get 8 oxygens over here. The only compound I have that has oxygen in it is water. And so to have 8 oxygens, each water has 1 oxygen, so I'm going to need a total of 8 water molecules. And in 8 water molecules, there is a total of 8 oxygens. However, this 8 does not only apply to the oxygen, it also applies to the hydrogen. So 8 times 2, there's 16 hydrogens here, and there's 18 here. So 16 plus 18. So I actually have 34 hydrogens in the products. That's a lot of hydrogens. So now my carbons are balanced, my oxygens are balanced, and the hydrogens are not. So I need to make this 2 a 34. And I'm going to do that by messing with this hydrogen right here. Now each one, since the homonuclear diatomic, has 2 hydrogens to it. So what number times 2 is 34? 17. And that makes me have 34 hydrogens. And I know that 17 feels really big compared to some of the ones we balanced, but it's right because all of our atoms are balanced out. Number 10, we're doing the same thing, except this time they give you a word problem and you have to write it out. And the directions tell you to make sure that you balance it and include the phase symbols. So the first one, it says solid iron, and it has, if you'll notice outside it, parentheses and a 2. So it looks like this on your book, solid iron and 2. This is a time for you to remember when we were writing ionic compounds, if we had a transition metal, which is a metal in that middle section of your periodic table, its charges can change. And we note its charge in parentheses. So that 2 does not mean there are 2 irons. It's just telling me the type of iron. Yes, there are more than one type of iron. And then it says, so it's solid iron 2 sulfide. So this 2 tells me its charge is 2 plus. And sulfide is a sulfur. And if you'll know, when we go from a name to formula, we have to balance the charges. And sulfur has a charge of 2 minus. How do I know that? I don't have my periodic table up here, but on your periodic table, you should have written some of those numbers above the column. Sulfur has 6 valence electrons, so it's wanting 2 more. So it's going to pull in 2 more. And so if iron has 2 plus and sulfur is 2 negative, these actually would balance out their charges, and so I wouldn't have to do the crisscross method where I adjusted the subscripts down here. So it's iron, sulfur, and it is a solid. The other part of the reactants is telling me it's reacting with oxygen in our air. Since it's in our air, I know it's a gas, and oxygen is that homonuclear diatomic. So don't forget that it's always O2 in air. Now, it tells me that it's making iron 3 oxides. We have to do this again where we have an iron and it has a 3 plus charge. It's the charge on it. That is not how many irons. And then I have oxygen, and oxygen is a 2 minus. So if you'll remember that these charges don't balance out, so I have to alter this equation or this formula so that I have balanced charges. And the trick that we had was we did a crisscross. Now, if I have 2 irons and each one is a 3 plus charge, iron's going to have a total charge of 6 plus. And for oxygen, I've got 3 and each has 2 negative. So it has a total charge of 6 negative. So this is going to be a balanced compound, and it tells you it is solid. The other thing that it tells you it's producing is gaseous sulfur. dioxide. That di in there, I know that it is a covalent compound. Covalent compounds, I don't have to deal with charges. I just have 1 sulfur and 2 oxygens. And this is a gas. I'm running out of space. I always start too far over on the board. So now let's balance it. We have iron, sulfur, and oxygen. And I'm going to do oxygen last because oxygen's by itself. And for irons, we have 1 iron. And I also have 1 sulfur. And I have 2 oxygens. Down here, I have in this compound 2 irons. And if I'm looking at sulfurs, it's only down here, so I have 1 sulfur. And you're gonna find oxygen in both compounds of the product, so we've gotta figure them out for both and add them together. So I've got 3 oxygens here and 2 here, and so that makes a total of 5 oxygens. It doesn't matter if I do iron or if I do sulfur first, just gonna save oxygen for last because it's by itself. So with iron, I'm gonna do it first because it's on top. So I have 2 irons down here. So I have to have 2 here. So I'm gonna put a 2 in front, and that gives me 2 irons. Now this 2 also changes this sulfur to 2. My sulfurs were balanced, but they are not anymore. So now I have 2 sulfurs and 1. So I'm gonna change down here to being 2. I'm gonna do that by giving myself 2 of this compound, right? That means I have 2 sulfurs. But not only did it change the sulfurs, it also changed the oxygens. So each compound has 2 oxygens, and I have 2 of that compound, so I have 2 times 2 is 4. So we have 4 oxygens here and 3 here. So now we have 7 oxygens. All right, now this is where this problem gets a little weird. So to make it simple, I have a 2 and a 7. Can I make this 2 into 7 oxygens? I can technically if I put 3.5 here. Why? 3.5 times 2 is 7. So if I did this, yes, I would have 7 atoms or 7 oxygens. But technically, each of these coefficients tells me the number of atoms or the number of molecules. So like I have 2 of this iron 2 sulfide. I have 1 of Fe2O3 and 2 of sulfur dioxide. I cannot have half of an atom. It's not possible. I can only have it in whole numbers. So that you can get this in a whole number, the trick that we do is you take all your coefficients up here and you multiply them by 2. And I'll show you what I mean. So instead of a 2 here, I multiply it by 2, this becomes a 4. If I take 3.5 and I multiply it by 2, this becomes a 7. See, now I have a whole number. 1 times 2 becomes a 2. And 2 times 2 becomes a 4. So that got rid of that decimal there. And technically everything got multiplied by 2. So now we have 4 irons, 4 sulfurs, and 14 oxygens on each side of the equation. So you would do that over there too. And that is how you balance one, where you end up with a decimal. And it's usually the oxygens that you end up with, like a 1.5 or 2.5, and you have to multiply it by 2. You're going to see that on your oxygens. Question 11, they give you the balanced equation, and it's kind of a different type of equation, but they want you to say how many of each molecule are used up, and then how many of each molecule are made. Well, we're using up the reactants, and so we're going to be, how many of this molecule do we have? Well, I have 1 molecule of TiCl4 is used up, and I'm also using up 2 molecules of water, and I am making, what I am making is, for this molecule, there's not a coefficient there, so it's understood 1. So I'm making 1 molecule of TiO2, and I am making 4 molecules of HCl. I think what this question is wanting you to do is making sure that you understand that the coefficients are equal to a molecule, so that this means 2 water molecules. For the next part of chapter 6, we're going to focus on types of chemical reactions. And right now in this part, there's 4 main types of chemical reactions. You're going to add on a few as you move throughout the course, but these are the 4 for this chapter. Now this book does something that's a little bit different, and it has the first reaction you learn is called a formation reaction. And a formation reaction is when you're taking compounds or elements and you're sticking them together, you're forming something. I take a sodium and I take a chlorine and I stick them together and I have sodium chloride, right? Or I take a hydrogen and oxygen and put them together and you get water. That's a formation reaction. But what this book does is it calls it a formation reaction. Most other texts, so if you take chemistry in college, it's probably small, so it's probably hard to see it. They'll refer to this as either a synthesis, because when you're synthesizing something, you're making it, or sometimes you'll hear this referred to as a composition. If you're composing something, you're making it up. But a formation reaction is just taking 2 things, putting them together and forming something. The other reaction we get is a decomposition reaction, and it is the total opposite of a formation reaction. Instead of making something, if you'll know when something decomposes, it breaks apart into its components, just like if you put a banana peel outside, it would decompose. A decomposition reaction is you're taking a molecule and you're breaking it into its parts. You're just breaking it up. Now the other 2 reactions get a little confusing to people. We have a single displacement reaction and we have a double displacement reaction. For a single displacement reaction, you have a compound and you have a lone molecule, and it's almost like this lone molecule comes in and pushes out the other part of one part of the compound. It's like, hey, my turn, your turn is over, I'm coming in, and it kicks one of them out. That's a single displacement. One element came in and displaced, which is like removed another element. The other one that you're going to see is called a double displacement. And the best way that I can think of to explain a double displacement is if you have like 2 couples on the dance floor, if you're ever in a dance class and they say, change your partners, right? And so you swap. You break apart from your couple and you swap partners into your new dance. And that is really what is happening in a double displacement reaction. For comprehension check question number 12, they want us to give a formation reaction, and that's a synthesis where you take the parts and you add them together, and it tells you the product is HNO3, and we're always going to balance them. So it tells me this is what I'm making, and if it is a formation reaction, you're going to be taking all the parts. Well, so I need a hydrogen, the homonuclear diatomic, it's going to be H2. I need nitrogen. Nitrogen's a homonuclear diatomic, so I also need 2 of it. And oxygen, which is also a homonuclear diatomic, so you need 2 oxygens. Now this is the basis of this formation reaction, but it is not balanced. So on the reactant side, you have 2 hydrogens, we have 2 nitrogens, and 2 oxygens. It's pretty easy to figure out. And on the product side, I have 1 hydrogen, 1 nitrogen, and I have 3 oxygens. So now I'm going to balance it. As far as to what you do first, for this it doesn't really matter, because if you'll notice on this side, we have each of these elements alone. And so we're going to first look and see what we got to do. So I need more hydrogens on this side. So in order to turn this into 2 hydrogens, I'm not going to change the molecule. Remember, I'm not messing with subscripts, but I only change the number of molecules I have. Now this gives me 2 hydrogens. It also affects the nitrogen. And since each molecule has 3 oxygens in it, I now have 6 oxygens. So my hydrogens are balanced out, my nitrogens are balanced out, and the only other thing that's not balanced out is oxygens. Since I have 6 over here, this needs to become a 6. So each molecule has 2, so 3 times 2 would give me 6. So this is the balanced out formation reaction for HNO3. For question 13, it looks a little intimidating at first, but I'm giving two equations and it tells me to identify one as either single displacement or double displacement. And so when you're looking for a single displacement, this is the picture that I'm using for this. And you always have a compound and a single element. And what happening is this single element is coming in and taking the spot. And so if this is the metal and this is a metal, it's going to be replacing it. So like one metal comes in and replaces the other metal. And you're going to see this down here. I have silver in a compound, right? Silver is a metal. And then I also have sodium in a compound, or sodium alone, and it's a metal. And so what is happening is sodium is coming in and it's kicking silver out and it's taking silver's place. So in the end, we have silver alone and sodium took its place in the compound. And this is called single displacement. One element is being pushed out. That's the single part. I know that's messy, but that's what this is. Now this one, you have two compounds. So that's a hint. We have AgNO3 and NaCl. And this is, you haven't been trained to look at it yet, but think of this as one compound, all right? This NO3. So like I said, this is the one, this is the double displacement. This is the one where it's like each of these are on the dance floor and they're told to switch partners. And so they're gonna switch the metals. And so silver leaves NO3 and goes to be with chlorine. So you have silver chloride. And the same happens, sodium leaves the chlorine and goes to be with NO3. It gets a little bit hard to look at these to tell them apart. So when you're looking for single displacement, you're looking for this lone atom out here that's gonna push in and take its place. When we have double displacement, you're looking for two molecules. For the last one of this comprehension check, we actually have, and I just realized I didn't have it on there, a type of equation called combustion. And if you're familiar with a combustion reaction is like you're burning stuff. And in order to burn something, you need oxygen. So all combustion reactions happen in the presence of oxygen. So you're going to be looking for some compound, and we're adding oxygen to it, and it's a gas, and you're burning it. Now, all combustion reactions have either incomplete combustion or complete combustion. If it's what we call complete combustion, the products are always going to be carbon dioxide and water. That means that all of whatever we had here is combusting, completely consumed. And so for question number 14, it says to give the balanced chemical equation for the complete combustion of hexane. And so complete combustion of hexane would be, hexane is C6H14. And a complete combustion reaction always reacts with oxygen and it always produces CO2 and water. That is something you need to learn. You need to write it down on your note card. The other option you have is when you have a combustion reaction, let's say it doesn't completely combust in like perfect ratios. This is really what happens in real life. And when this happens, you're left with like black sooty stuff left over or ash of a combustion reaction. So if we had an incomplete combustion reaction, and yes, I know these are not balanced, it doesn't only produce carbon dioxide and water. In an incomplete combustion, you're going to be producing carbon monoxide and water. And this is actually a very poisonous gas to breathe in. You probably have a carbon monoxide detector in your house to make sure that like your gas is not leaking carbon monoxide into your house. Because if you had this leak, you cannot smell it. It does not have that weird gassy smell. And it also does not have any color to it. So if it got in your house, you would not know it. And what it does into your body is it makes you tired. So you would just feel like you needed to go take a nap. You would lay down to take a nap. This bonds to your red blood cells instead of oxygen, and you would never wake up. So most houses that have natural gas that comes into them are gonna have a carbon monoxide detector in their home to make sure that you're not getting incomplete combustion and you're getting this poisonous gas. Another product of incomplete combustion is carbon, and this is just elemental carbon by itself. And this is going to be your soot or your ash, that black film that you may see from things. And this is also a product of incomplete combustion. This happens if, say, you're not having enough oxygen coming in. This can happen in your car if you don't have enough oxygen coming in for the product. But I do want you to recognize the difference between complete and incomplete combustion. But question number 14 wants us to write the balanced equation for complete combustion. So complete combustion, we have the carbon hydrogen compound that they give us, and I know it is reacting with oxygen to produce carbon dioxide and water. And if you don't remember that, write it on your note card. That is the products of complete combustion. And so now we're going to balance it. As usual, I'm going to balance the oxygens last because it's alone and it's easier to mess with at the end. And so the first thing I'm going to do is carbon, and I have up here 6 carbons. In my reactants and in my products, I only have 1 carbon. And as hydrogen goes, I have 14. And in my products right now, I only have 2. And as for oxygen, I have 2. And down here, I have 1, 2, 3 oxygens. So nothing is balanced. The first thing let's balance is the carbons. Since I'm starting with 6 carbons, I have to end with 6 carbons. So I'm going to have 6 CO2 atoms or molecules produced. And that makes that have a 6. But it also affects the oxygen. So I have 6 times 2 is 12, plus that one is 13. So let's see now. Saving oxygen for last. Let's do hydrogens. I need to get way more hydrogens in the products. And so to get 14, since there's 2 hydrogens in every water molecule, I need 7 water molecules. And that will give me a total of 14 hydrogens. That also affects my oxygens. So 7 oxygens down here plus the 12 gives me 19. My carbons are balanced, my hydrogens are balanced, so I'm left with my oxygens. So 2 times, I've got 2 oxygens in each molecule. So how many molecules do I need to get 19? But it would actually be 9.5, because 2 times 9.5 is 19. I hope you remember the problem with this is I cannot have a decimal. This has to be a whole number. I cannot have half of an oxygen molecule. So I'm going to multiply everything by 2. So we have 2 of this. This times 2 becomes 19. 6 times 2 becomes 12. And 7 times 2 becomes 14. And so then all of these would multiply by 2, and that is the complete combustion hexane. And so remember, a complete combustion, you react it with oxygen and you produce carbon dioxide and water. All right, I'll see you on the next video for the end of chapter 6 review questions.